section 1.8 today, which talks about functional transformations. Now, transformation is just when you're going to change the graph of a function by changing its equation. So we start with our basic functions, and then we start to add things to it, changing what it looks like, and that will change what the graph looks like. So if I think about a function, let's say I have an absolute value function. We all know that looks like some kind of v. But now if we start changing it, so let's say I add a 2 inside the bars, or I subtract a 3 outside. That'll change what the graph looks like. It'll still be some kind of v, but it'll look like a different v. So our goal is to kind of investigate what changes the graph when you change the equation. So in general, we'll start talking about shifts, vertical and horizontal shifts, and then we'll talk about dilations, and we'll talk about reflections. So we'll talk about vertical shifts. We'll talk about shifts more than transformations. They're all transformations. But a vertical shift is when you're going to move a graph up or down. And I'm going to say it is k units. So I'm going to add or subtract a k to move it up and down. The question is, where do you add it? So in general, if I take a function, f of x, I have an inside of the function, which is inside the parentheses, and then I have an outside of the function. So if I add k, it is going to actually move up k units. So if I add it to the outside of the function, it's going to shift it up or down. So if I do a specific example, let's do a cubing function. So if I have x cubed plus 3, that is going to shift up 3 units from the original cube function. So we can also have horizontal transformations, and horizontal transformations or shifts are obviously going to move it to the left or the right. So horizontal will work basically the same way. So it's going to move a graph left or right. The only difference is it's going to work a little differently than the vertical because we can't do it on the outside. It's the same way. But we'll say by h units. And the way it works is we say y equals f of x minus h. So this is happening inside the function. And you also notice that it says minus h, so it's always the opposite of what you see. So if I go back to my cube function, if I do x plus 2 cubed, this is actually going to shift 2 units left. Now generally we think of positive 2 as going right, but because it's minus h, this is technically written x minus negative 2 cubed. And so the h is actually negative 2. That is why it moves to the left. But you always want to think about it. If it's inside the function, inside the bars, inside the parentheses, then it always moves the opposite way of that sign. So plus will go left and minus will go right. So what we can do with these transformations is we can sketch graphs really quickly. So here are a couple examples, one absolute value and one square root. So I want to list the transformations and then I want to kind of sketch my graph. So in this one, you can see the plus 6 is on the outside. So that's going to be a shift up by 6 units. Now, if you shift something up and down, obviously up and down, that is going to influence the y value. Anything left and right will influence the x value. Anything up and down will influence the y value. So if you consider our base function, so if I just go back to our first section when we did the square root of x, I know it looks something like this. And it has some points on here, 0, 0, 1, 1, 4, 2. And you can verify those because The square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. So to those, if I want to do it really formally, I'm going to add 6 to only the y values. So 0, 0 will become 0, 6 because I'm adding 0 to the y value. And this will become 1, 7 because I'm adding 6 to the y value. And this will become 4, 8 because I'm adding 6 to the y value. So my new graph looks something like this. So if I were to graph this function and say Desmos or something, I would see these two graphs. And so I would see that it gets shifted up 6 units from the original. Because again, it's always the opposite sign when you're doing on the inside. So if I think about my regular absolute value of x, then if you recall, we have some points on here, 0, 0, 1, 1, negative 1, 1, all these are on there. So that is going to make our V shape. And again, since we're moving to the right this time, I know that's going to affect my x value. So I'm going to add 2 to all my x values. So that's going to give me the point 2, 0, because 0, 0, plus 2. And then I'll get 3, 1 when I add 1 to that. And then if I add 2 to negative 1, I'll get 1, 1, which would look like this. So I'm just adding 2 to all the x values because it's a left-right shift and that's horizontal. So it looks like this. And I think you can agree that moving from the green to the black, we are certainly moving it to the right by 2 units. Shifts are a really big part of transformations, but they're only one kind of transformation. The second one we're going to look will be dilations. Okay. So a dilation, a stretch or compress, this is when we're going to make it, we're going to stretch it or we're going to compress it. So a stretch is going to kind of pull it either vertical or horizontally, and a dilation or a compression is going to push it together. So a vertical dilation is going to stretch or compress our graph vertically. And again, vertically obviously means with the y. Now the way we do this is if you take a function y equals f of x, if I want to dilate it vertically, I multiply an a out in front. I multiply some real number a. Now we're going to assume that a is just some positive number because a negative a will do something a little different. So in this case, if a is greater than 1, then we stretch the graph. It stretches it so it'll almost get pulled vertically. If a is somewhere between 0 and 1, so like 1/2 or something, it is going to compress it. It is going to get pushed down. So you have a vertical stretch and you have a vertical compress, really depending on that a. And a horizontal dilation will do the same thing. We're going to stretch or compress our graph horizontally. Now the way we'll do this is we still have our function y equals f of x, but now I'm going to put it as b. I'm going to put a b in front of the x. Now, the vertical dilation is no problem. We're just going to multiply the y's by a. It's not a big deal. But a horizontal is going to work really backwards, just like a horizontal shift work backwards. So if b is greater than 1, it is a compression horizontally. And if b is between 1 and 0, it is going to stretch it. And the reason is because if b is going to be bigger than 1, it is actually going to do something a little different to the x values. We're actually going to multiply them by 1 over b. So that's different. For the y's, I just straight multiply by a, no problem. But for the x's, I have to multiply by 1 over b. So this, and don't worry too much about the stretch and compress, because you can talk about vertical stretches and compresses and horizontal stretches and compresses being related to one another. But essentially, this is what the graph will look like. So if I look at these two examples, I have a squaring function. Now this one I'm multiplying on the outside, so that's a vertical dilation by 3. And then the other one is obviously going to be on the inside, but let's do this one first. So this is a squaring function. So if I do a squaring function, you know the point 0, 0, 1, 1, 2, 4. These are all on my graph. Looks like this. So if I wanted to get my new graph, and again, this is something you could certainly graph on Desmos, but just to kind of do it by hand, we'll multiply all the y's by 3. So 0, 0 will still stay 0, 0. 1 will become 1, 3 because you're multiplying the y by 3. And then if you do 2, 4, 4 times 3 is 12, so we'll get 212, which is way up here. So this is my new graph. So you can see how it's really compressed together. It's been stretched out vertically. So if you think about taking the black graph and pulling it up vertically, it has been stretched by 3. You can also think about it pushed together, but that's more of a horizontal thing. So if you think about it vertically, you want to think about pulling it up or pushing it down. And the opposite for horizontal. All right. So this one, we have a horizontal dilation because it's on the inside. Now, the trick about this one is it's horizontal dilation by 2. But the trick is, since it's on the inside, everything works backwards on the inside. We're actually going to multiply the x's by 1/2. So let's go ahead and see what this looks like. So we already did our square root function, if you recall. 0, 0, 1, 1, and then 4, 2. So those are my original points, right? So if I want to, and maybe I'll just write these to the side because this is going to get pretty cramped. So remember, I'm multiplying all the x's by 1/2. So this will still say 0, 0. This will be 1/2, 1. And this will be 2, 2. So I'm multiplying all the x's by 1/2. So I'm going to have to zoom in here to kind of plot these because they're going to get really close to one another. So 0, 0, 1/2, 1, and then 2, 2. So you can see it's going to kind of go this way. So remember, this b was bigger than 1, so it's kind of like we're compressing it. So if you think about pushing this black one back this direction, it kind of gets bent, and that's how we get this green one. So that is how we would do a horizontal dilation. The horizontal dilation is by far the weirdest because you have to remember to do multiplying the x's by the reciprocal. All right, let's look at some other types of transformations called reflections. Now, reflections are where you're going to flip the graph one way or the other. So a vertical reflection is going to flip the graph over the x-axis. So if I start with a absolute value function, if I want to flip it over the x-axis, all I'm going to do is I want it to look like this. And the way this happens is if my original function is absolute value of x, to make it flip over the x-axis, we just add a negative in front of the function. So this does what's called a vertical reflection. A horizontal reflection, same idea, except for going over the x-axis, it's going to flip the graph over the y-axis. So if I start with a different type of function, let's say I start with a logistical function. So here's a logistical function, looks something like this. So this is f of x equals 1 over 1 plus 10 to the negative x. So if I want to flip it over the y-axis, the flip version is going to look something like this, where kind of everything gets flipped to the other side. And the way we do this is we look at the x value, whatever the x is, and we just change the x to the opposite sign. So this would just be 1 over 1 plus 10 to the x. So the negative x becomes the opposite sign, negative x just becomes positive x. So there is our reflections. So if we look at these, we have one of each. So if we look at this, we have the inside, this one's inside, so this is a horizontal reflection. And remember, anytime you're doing horizontal stuff, that is going to influence the x. So when we do this, we have a square root function, our original square root function, 0, 0, 1, 1, 4, 2, kind of looks like this. There's my original square root function. We did that one before. So all I'm going to do is I'm going to turn all the x's negative. So 0, 0 will become 0, 0. 1, 1 will become negative 1, 1 because I just changed the x value. In a horizontal reflection, the x just gets replaced with negative x. And then negative 4, positive 2 for that last one. And then it looks something like this. So if you flip it over that axis, so our black was our original just square root function, and now this teal one is our square root of negative x. Now this last one has two negatives, so it has a negative on the inside and a negative on the outside. So this has both a horizontal and a vertical reflection. Now I did both of them just because you can see that sometimes reflections are very helpful and sometimes they don't do much. So this one's x and this one's y, because vertical always reflects the y and horizontal always influences the x. So we start with an absolute value, so we've done this one before. So if I think about some points on an absolute value graph, negative 1, 1, 0, 0, 1, 1, and you can just think about, because the absolute value of negative 1 is 1, absolute value of 0 is 0, absolute value of 1 is 1. So I'm basically going to change the x and the y to the opposite side. So that's going to make this 1, negative 1. It's going to make it 0, 0, and it's going to make it negative 1, negative 1. Now, interesting, what you kind of see here is the y values definitely changed. They were 1, 0, 1, and now they're negative 1, 0, negative 1. But the x values actually are the same. They're in a different order. They were negative 1, 0, 1. Now they're 1, 0, negative 1. But it's the same exact point. So in this case, if I plot these, you can definitely see the vertical reflection because it flips over, but you don't really see the horizontal reflection. Reason being is if I have a V and I flip it on the other side of the y-axis, it's going to look the same thing. So that is why sometimes the reflections don't do anything, because if you flip it on top of itself using its symmetry, it ends up being the same. So those are our big 6 transformations: 2 shifts, 2 reflections, and 2 dilations. Some kind of So let's just look at a combination of these. We want to list the transformations, and then we kind of want to sketch our graph. So this first one, I have 3x minus 2 plus 1. So remember, every little part is going to be a transformation that we're going to have to do. So the 3, the 2, and the 1 will all do something. So we always usually start inside the parentheses. So that's a minus 2. So that's going to be a shift to the right of 2 units. And again, don't forget, when it's inside, it's always the opposite of what you think. So minus actually goes right. Then I'll typically do the number out in front. So that is going to be a vertical dilation by 3. And then the 1 outside is obviously, it's added, so it's going to be a shift up 1. So we're moving it right 2, dilating it by 3, and shifting it up 1. And just to remember, since it's a shift left and right, that's affecting the x. Vertical stuff is y, and shifting up is y. Now our base function, our parent function, remember, is just the squaring function. So I'm going to start with that. So I have 0, 0, I have 1, 1, and I have 2, 4. And I know there's 2 halves to this parabola. It'll look something like that. So what I like to do, you can do it any way you want, but when we're doing these multiple transformations, I like to write these points. And then I'll do what I'm going to do everything that I have to. So for example, the only thing with the x is shift right 2. So I'm just going to add 2 to all the x's. So that's going to be 2, 3, and 4. So you can almost envision that's going to move all those x values to the right, and that's going to make our graph over there somewhere in the first quadrant. Now, as far as the y's, I have a dilation by 3, so I'm multiplying by 3, and then I'm going to add 1. So I'm going to take 0 times 3. 0 times 3 is 0. 0 plus 1 is 1. For the second one, I have 1. 1 times 3 is 3. 3 plus 1 is 4. And then I have this 4. 4 times 3 is 12. 12 plus 1 is 13. So those new points are pretty different. So we have 2, 1, and we have 3, 4, and then we have 4, 13, which is way up here. So you can kind of envision our graph is going to look something like this. So let's just take a peek at it. It's definitely shifted to the right from the teal one. It's definitely shifted up 1. And that dilation, again, is just kind of make it narrower or wider. In this case, it's much narrower. But I picked out the transformations. I figured out if they were x and y. And then I just found some generic points on the graph and used those. All right, let's look at the next one. So this one is a cube function. You can see that the starting is a cube function. And if you're ever confused how to get those starting points, you literally can pick any points you want. 0, 1, negative 1, 0, 1. Negative 1 to the third is negative 1, 0, 1. I could pick 2 and get 8, because 2 times 2 times 2 is 8. Whatever you want. So here is my basic cube function. If you remember what that looks like. So there's my base function. And now I'll just start picking out transformations. So inside I see a plus 2. So that's going to shift left by 2. So that's going to be a change in the x. Nothing else inside, so everything else will be vertical. We have the negative out here, so that's a vertical reflection. So that changes the y's to negative. And then we have the shift up 5. So that's going to take the y's and add 5. So you can almost envision what's going to happen to this graph. It's going to move left, it's going to move up, and it's going to be upside down. But if you take our points, if we take those starting points we had, negative 1, 0, 0, any points you want are fine as well, 2, 8. So when I change them, the only thing for the x is I'm shifting left 2, so I'm subtracting 2. So that's going to be negative 3, negative 2, negative 1, 0. And for the y's, I'm going to turn them negative and then add 5. So negative, negative 1 is 1. 1 plus 5 is 6. 0 becoming negative is still 0. 0 plus 5 is 5. Negative 1 turning negative is negative 1. Negative 1 plus 5 is 4. And then 8 turning negative plus 5 is negative 3. So these points should be on my graph. And the nice thing is you still do have a Desmos graphing calculator. You're certainly welcome to plot it and make sure these points actually are on your graph. But as you will see, they certainly are. So I'm just plotting those points I had. 0, negative 3 is down here. And I know it has to be the same kind of squiggle shape, so there you go. So you can see that that teal graph has definitely been moved left. It's definitely going the opposite way, and then it's shifted up by 5. So write your transformations, do them step by step, and they work out pretty nice. And again, don't be afraid to use Desmos It is a great tool to check these. All right, so this last one is an absolute value one. Nothing too crazy about this one either. So we can start with our absolute value function, which again, if I just want to pick some points, negative 1, 0, 1, 1, 0, 1, because it makes everything positive. I feel like we've done this graph several times. So it looks something like this. I'll make this black one the parent function. So if I look inside, I have this minus 1, which is going to be a shift right by 1. So that's going to be the x is adding 1. The 2 is going to be the vertical dilation, where we're taking the y's and multiplying by 2. But this negative out front also is something. That's a vertical reflection. And vertical reflection, remember, are going to turn the y's negative. So really, you can see we're adding 1 to all the x's. So if I take those original points I had, the only thing I'm doing with the x's is I'm adding 1. So that's going to become 0, 1, 2. And then we're multiplying by 2 and turning it negative. So I'm really multiplying by negative 2 if you take these two together. So multiplying by negative 2 would be negative 2, 0, negative 2. So let's plot these, 0, negative 2, 1, 0, and 2, negative 2. It's still an absolute value, so it still looks like a V. So you can definitely see how this is shifted to the right. It's definitely upside down and a little harder to see, but it's definitely skinnier. The red one is definitely skinnier than that black graph just because we multiplied everything by 2. All right, let's go ahead and look at one more. This is just some generic graph I made up, and then we can do some transformations on it as well. So if you look, so this is the graph of f of x. So you have all these different points on here. And we want to try to figure out what the graph of these would look like. So f of x plus 2, we're trying to basically take this graph, which is f of x, and find f of x plus 2. Let's just say shift up of 2 units. So that's going to be adding 2 to all the y's. So if you think about what some of these points are, like this point is negative 4, negative 2. I'm just picking some good points off my graph. 0, 5 is a good point. Maybe 5, negative 4. And then maybe 10, 0. Those are good kind of key points for this graph. So all I'm doing is shifting them all up 2. I'm just adding 2 to all the y's. So if I add 2 to all the y's, I'll get negative 4, 0, 0, 7, 5, 6, and 10, 2. So if I plot those points, there's negative 4, 0. Let me make this a little bigger. 0, 7, which is up here. 5, 6, which is here. And then 10, 2. 10 up 2. So something like that. So if I want to make it look like the same pattern, I know it has to kind of go up in some direction like this. And then it's going to flatten out. Oh, I see what it is. So this one is 5, negative 4 to start with. So then it's going to be 5, negative 2. So that would make more sense. So ignore that one. So 5, negative 2 will make the graph look more like what it's supposed to. So it goes here, and then it goes back up, and then it continues down. So again, you got to start with the right points or you get the wrong graph. So there you go. So you can see that teal graph looks the same as that black graph essentially, except for it's been shifted up 2 units. All right, let's look at the transformations on this last one. We have plus 2 on the inside, so that's going to be a shift to the left by 2. So that's going to be taking our x's and subtracting 2. And the negative out front, again, that's a vertical reflection. And a vertical reflection is going to be when we turn the y's negative. So if I think of those same points I had before, I had the -4, -2, the 0, 5, the 5, -4, and the 10, 0. If I apply these transformations, I should see a graph that is shifted left 2 and flipped over the x-axis. So I'll subtract 2 from all these, -6, -2, 3, 7. And then I'll turn all the y's negative. So 2, -5, 4, 0. Now I had no idea what this graph was, but I just picked points off of it, and I started plotting them. So there's 0, 5, 0, or sorry, -2, -5. I'm looking at the wrong column. Yeah, we'll say that's 5. And then 3, 4, so over 3, up 4. And then 7, 0 is here. So normally we started going up, so this graph's going to go down, and then up, and then down, and then continue. So I'm just trying to continue the pattern. So you can see that this graph is definitely upside down. Kind of hard to see that it's shifted over 2 units to the left, but it is. You can kind of see by this starting point and this starting point. One's at -4 and this one's at -6. So you can kind of see that. So just a little bit about transformations and how we work with those. And we'll obviously do lots of practice here, figuring out lots of different types of graphs.